All right, people, I really appreciate you coming, and I hope you won't regret it. So because actually, why I decided this time not to invite some famous mathematician or physicist or computer scientist to our graduation ceremony is that, I think this is quite a breakthrough. I mean, mathematically, it is available to an advanced undergrad or to some people from the circle who are as advanced as some advanced undergrads. But I think it's quite a breakthrough in both game theory and social sciences. And it is a surprisingly simple model that explains at least a little bit what I, until last night, perceived as irrationality of the world around us. There is nothing irrational, and our emotions just kind of muddy our thinking, and we don't see the simple math that explains forever wars that we keep witnessing, participating with our taxpayers' money and whatnot. So, first, I originally started working on this, looking at this ongoing war in Iran, just trying to rationalize for myself what's going on, why are we doing what we are doing. Turned out this kind of mechanism of social mechanics, it is way more general and describes a lot of things. And it's surprisingly simple until you get to quantum stuff, which I probably wouldn't have time for in this lecture. So let's get started. First of all, what is the beginning of this typical modern day war, and what are the players? As usual in game theory, we can have more than two players, but most of the models have just two players. For example, an investor playing against the market, or a person playing against the world, or in this case, it's a war, there are two sides, there are two players. Player one, a modern democracy or a block of such. P2, a regime antithetical to P1. The stated goal of the war is to liberate, whatever it means, I don't analyze the word, the people suffering under the rule of P2. Now, here comes the funny part. The force P1 can apply is limited from above, because an easy way to win in each of these complexes is just to destroy a large part of the double-use infrastructure, but that will cause massive civilian casualties, which is not acceptable to the public opinion of P1, and this war is alive as long as public opinion is neutral or supports it. So the actions of P1 are severely limited from above. But the same is true for P2. They don't care usually about public opinion, but if they make an aggressive move, they can trigger a strong response from the other side. And since the other side is much stronger militarily, economically, and whatnot, P2 is also limited. So this results in all of these wars, not just the ongoing one in Iran, but all the previous ones, if you look at Afghanistan, Iraq, you name it, they all look like a multi-round game of chicken. Now, I hope that sounds familiar, even if you completely are unfamiliar with game theory. You watch the news, and the first thing when you watch this strange war with Iran, the first idea that comes to everyone's mind is they're playing the game of chicken, both sides, even if you don't know what it is. So with this in mind, let me kind of switch my hats from an observer to an analyst. So I imagine that there is some war planner called up by those top generals, and what are the questions they would or you would ask from a war planner? The first question is, who is going to win? Now, obviously, a war is a random event. Nothing is guaranteed for sure, but there are likelihoods. So in mathematical terms, what they're asking for is, okay, if we start this war, what is PW, our probability to win it? You can give it in percent, so as a decimal number, but we want to know our chance to win. If it's close to 100, good for us, 100%. Second thing that comes to my mind, I would ask, what is the chance of a stalemate, of a draw? Sure, in math language, find the probability of that stalemate. The third thing is, how long would that war take, right? If it takes a week, I mean, for this side, obviously, they want to finish it up before midterm elections. So it would have been good to know that there is a good chance. But the stopping time of the game is a random variable. So we cannot give those generals a precise answer. You can give the expectation of the answer, right? So in math language, find the expectation E of t of the stopping time of that war. Okay, the next question. What does P1 player 1 have to do to win? And finally, suppose here comes an analyst, your humble servant in this case, and I will answer all these questions precisely, with great precision. It's mathematical theorems. They cannot be untrue because I have proofs. And then I will look back and you will look back with me and you will see that it kind of doesn't look good. So the next question you should ask me, okay, is there a better way? If the above doesn't look promising, is there a better way? The answer is yes, but for that we have to switch from the classical realm, from the classical game theory to the quantum game theory. And I have some partial results in there as well. In particular, I have a strategy for P1 to win for almost sure, with probability 100%. But I don't really understand what this quantum algorithm means in real life. And there are other quantum things, and we are working on it. But I think here is this huge door opening. And the big question is, like, what does it even mean? Is it realizable? And if so, can we use it as player 1 to our advantage? So here I will need a little bit of math. But before I switch to math, any questions so far? No. All right. So here is this classical game of chicken. So let me first comment on the slide, and then I'll do a couple of really easy computations. So how do we play the game of chicken? It's one of the simplest models in game theory, and this is how we play it. We have two roads and unregulated intersection. And we have two cars, equal size, driving towards that intersection. So it's not like one is an electric scooter and the other one is an 18-wheeler. In this case, it's a different game. It's two equally sized cars, and there are two drivers driving towards this intersection. There is no cop, there is no traffic lights. So what can they do? Each of the drivers has two strategies. Chicken out, it goes first because I think it's more rational, just in case, or drive through. So if both sides choose to chicken out, no feelings hurt, everyone gets 0 utils. And what's one util? One util is the measurement of your gain in a game. Whether it's a war or this exercise in driving through unregulated intersection, it could measure your pleasure, it could measure some material assets, doesn't matter. One util is 1 unit of whatever. So if they both chicken out, the payoffs are 0 and 0. And this table with numbers is called the payoff by matrix of the game. Now, if the first player chickens out and the second drives through, then the first player loses 1 util, probably hurt ego, and the second player gains 1 util because they feel superior. And of course, the game is symmetric, almost. So if the first player drives through and the second chickens out, the first gets 1 util and the second loses 1 util. Finally, if both choose to drive through, the first player loses L utils and the second player loses M utils, where L and M are large positive integers. L and M are much greater than 1. So this is a small change to the standard game. In the standard game of chicken that you will find in any game theory textbook, it's negative L. But for our war model, L and M are damages the sides inflict on their opponent each time they drive through. So, for example, as a war planner, I think, okay, I am player 1, so the damage I inflict on player 2 is negative M, and this is the parameter under my control. I can choose it. I can inflict more damage or less damage. But I cannot choose this parameter because that's what player 2 inflicts on me each time we both drive through and collide. So this is, for me as a war planner working for player 1, this is just a parameter of the game. Now, this game has 3 Nash equilibria, 2 pure and 1 mixed. I think that most of the people in the audience are familiar with Nash equilibria. Let's check. If you do not know what a Nash equilibrium is, please raise your hand. Okay, since some people don't, and this is going on YouTube, I'll explain. So, what is a Nash equilibrium? I'll not put it in writing, I'll just say it out loud, and the reason is we already have a video on our Math Circles YouTube channel where I specifically lecture about the game of chicken. And actually, its application to the war in Ukraine and something else. So you can see the details over there, but the definition is pretty simple. In this case, I'll limit myself to the case of this game, it's easy to generalize. A Nash equilibrium is a pair of strategies, one for each of the players, such that none of the players has an incentive to switch unilaterally. So how do you find it? Well, how do you find the pure Nash equilibrium? So let me quickly redo this table on the board. So chicken drive, 0, 0, negative 1, 1, 1, negative 1, negative L, negative M. So, and you will see why the words pure Nash equilibria and mixed Nash equilibria are used. So, okay, how do you find out pure Nash equilibria? You just think, okay, I'm player 1. So player 1 is traditionally here and player 2 is here. So I'm player 1, and I think if player 2 chooses to drive, to chicken out, what is my best response? So since player 2 is now only limited to chickening out, this part of the payoff table disappears. We only have one column. So I just look at my own payoffs in this case, and I compare these two numbers. One util is better than no util, so I mark it with a star, an asterisk, whatever you call it. Now I switch here. If the second player chooses to drive through, what's my best response to that action? I'm looking at these payoffs, and of course negative 1 is better than negative 1000. Of course the game is symmetric, so I can just put other asterisks by symmetry, but let me repeat this way of thinking to kind of make it easier to understand. Because player 2, they think the same way. They think, okay, if this dude in the other car chickens out, what's better for me? I'm looking at my payoffs, and these are the second payoffs. Well, 1 is better than 0, and of course negative 1 is better than negative M. So here are two pure Nash equilibria. So a pair of strategies, chicken drive and drive chicken. In this case, the payoff is negative 1, 1, and in this case, the payoff is 1, negative 1. Any questions? Pretty clear. How about that mixed one? Well, here comes a little bit of probability, and there are two ways to think about it. So what if I drive, first player chickens out with probability P and drives through with, of course, it's classical case, nothing quantum yet, probability 1 minus P. And this dude, of course, Q and 1 minus Q. And you may ask me, Oleg, where does this come from? There are two ways to explain. One is, how do you make your decision? You kind of, as you approach this intersection, you have an uneven coin, probably based on your previous experiences. And of course, it's not a physical coin, it's something you flip in your mind, right? Like random number generator based on something. But based on your previous experience, you flip the coin, and if it says chicken out, it does so with such probability. So you get heads with probability P, and you get tails with probability 1 minus P. If you get heads, you drive through. If you get tails, you if you get heads, you chicken out. If you get tails, you drive through. The same is true here. So that's one explanation. And the other is, if you play this game repeatedly many times, then these are the frequencies of your decisions. So given that, there is one more Nash equilibrium. And the way to think, there are two ways to think about it. So the definition of a Nash equilibrium is a pair of strategies such that none of the players has an incentive to switch unilaterally. So you start thinking for the second player, right? As a first player, what probability P of chickening out should I choose to make these two strategies indifferent for the second player. So the payoff in the case C of P, if they choose to chicken out, is going to be what? I'm looking at the payoffs of the second player now. It's going to be 0 times P, right? So 0 times P, so this 0 times that P, plus negative 1 times 1 minus P. And that equals to, what is it? P minus 1. And the expected payoff, if they choose to drive through, is going to be 1 times P plus negative M times 1 minus P. And that would be equal to, let's see, P plus M times P minus 1, right? So if I set these two numbers equal, it gives me an equation. Let's see. P minus 1 equals to P plus M times P minus 1. So P cancels out. I hope I didn't make a computational mistake. So please check if I get an answer different from this one, then I have messed up someplace and I'll correct myself. Because, well, let's see what we get. So 1 comes here, and here I have M times 1 minus P. Divide by M, 1 minus P equals to 1 over M. So P equals to 1 minus 1 over M. All good. So if I chicken out with this is a probability of frequency, and I drive through with the complementary one, then I make my opponent indifferent. They can choose this strategy or that strategy. The expected payoff is the same. And because the game is symmetric, replace M by L, you get the same for the second player. And these are the expected payoffs. How is that? Well, you can plug it in here, for example, right? Since the second player is indifferent and my probability P hat, the optimal one, is 1 minus 1 over M, I plug it in here. So it's P minus 1 that equals to negative 1 over M. That's the expected payoff. Sorry. So C of P hat equals to this, negative 1 over M. And the same is true if they do this computation for me. So I compute the expected payoff for the second player. He computes the expected payoff for me. This is the pair of our expected payoffs. So if we play this mixed equilibrium, and why is it mixed? Because it's P times C plus 1 minus P times D for the first player, and it's Q times C plus 1 minus Q times D for the second player. It's a weighted sum of the POS strategies here and here, where the optimal rational behavior corresponds to P hat equals to 1 minus 1 over M, and the rational behavior of the second player is Q hat equals to 1 minus 1 over L. So if they're both rational players, and in my model I assume they are, they choose these probabilities. Now, how do I know that the players are rational? It's actually, I think, a philosophical observation. See, whether you like or dislike a regime or a government or a president or whatever, it's actually tectonic plates moving. They think they have control. They have very little control, as you'll see from this lecture. They can use some things to their advantage. They can be smart, but in fact, they are forced to behave rationally very quickly. As soon as they start things, things have their own logic, and they force them to behave one way and not all other ways. You'll see. So these are the rational weights. And now we know how to play one round of the game of chicken in this classical setup. Any questions?
So about the public support, I mean, it could be that. So when talking about public support, you know, I guess both countries destroying a civilian infrastructure, I think, is a war crime, right?
Well, let's not get into that. Let's stick to like really simple math, because all these, you know, human things are just like aberrations on top of some really fundamental mathematical logic. And this is not a political lecture. This is not a military lecture. I want to show you the bare bones with all the unneeded stuff removed. And you will see that there is a lot of logic and there is very little control that we as the people or the government or whatever have once the events have started. Okay, then let me move on. If there are no more questions, let's move on to the next slide. And you will see soon. So here it's a very math-intense slide, but I'll explain what it means. It actually means what you just have seen. And I promise we will not have slides as intense any longer. Now, if you don't capture everything right here, please feel free to email me. I finished writing this paper actually today's morning, and I'll be happy to email it to anyone interested. And you'll see these formulas and many more. And if you want to participate in the project, it's going to grow. Because there are so many things. You'll see. Feel free to participate, especially if you are a math circle student, an undergrad, a grad student, or maybe a graduating grad student getting their PhD and going elsewhere. If you get interested, you're welcome. There is enough stuff for everyone. So what does this mean? How do we model that war? And again, I think it describes not just the ongoing war, but all the many previous ones. As soon as both sides play the game of chicken, here comes the model. Both sides start having some initial utilities, u1 of 0 and u2 of 0. And these utilities can mean different things. For player 1, which is a democracy, u1 of 0 is public support at the beginning of the war. For player 2, which is a regime, whatever that means, you can think that it's probably some stockpile of military hardware. When they run out of bullets, missiles, drones, whatever, they'll have to stop. And then they play the game of chicken repeatedly, round after round. So K is time, and let's say K is measured in weeks. You can measure it in months and days, whatever. I took a week because to me it looks like from the news, like every week we get some news. Think K equals 2 weeks wouldn't change things much. So how do we play? At each round of the game, the sides can choose to chicken out, right? And in this case, this probability PQ, look, the probability distribution is pretty simple. If both sides chicken out, P comes from here times Q that comes from here. So if at this round of the game the sides chicken out, that happens with probability P times Q, and the utilities do not change. U1 of K plus 1 equals to U1 of K, and U2 of K plus 1 equals to U2 of K. Right? So there are 4 possibilities. Any questions? Now, what if the first player chickens out and the second drives through? In this case, the first player loses 1 util. That happens with probability. Look, P comes from here, and 1 minus Q comes from here. So with probability P times 1 minus Q, the next value of the utility function for the first player is the previous minus 1. And the value of the utility function for the second player with the same probability is the previous utility plus 1. So what happens here? The first player drives through, the second chickens out. So 1 minus P for the first player, Q for the second player. So with this probability, the first player increases their utility by 1, and the second player decreases their utility by 1. And finally, if they both drive through, and instead of posturing, they get a round of real fighting, then each inflicts the damage L and M on the opponent. That happens with probability 1 minus P times 1 minus Q. And in this case, the number of utils of the first player is decreased by L, and the number of utils for the second player is decreased by M. However, P and Q are not just some random P and Q. They are these optimal values because both sides are rational players. Either on instinct or by means of this very same computation, they actually, P equals to P hat, which is 1 minus 1 over M, and Q is equal to Q hat, which is 1 minus 1 over L. And then they play this game, round after round, until the first of the players runs out of utils. And I don't mean P1, but the rules of the game are the first player to run out of utils loses the war. So now, let me get back for a sec. So what you're looking at, let me show you the next slide, right? Here are a few of these wars, 7 on each slide, modeled with various conditions using Wolfram Mathematica. So just to check that you guys follow, so what you see here, this red dot over here, is so the number of utilities of the first player is the x-coordinate. The number of utils, of the second player is the y-coordinate. Together you have xy, you have a point in the xy plane. And then at each round, the number of utils changes according to the rules I just have shown you. And the first player to run out of utils loses the war. So just to make sure that everyone understands, if we are here, who has won? Player 1 or player 2? Player 2, of course, because x is negative, right? So the number of utils, the public support at home is negative. The Congress is impeaching the president and all that, But these guys, they still have a couple of drones in storage. They have one. And here, for example, you see, out of the 7 wars fought in this simulation, player 2 always wins. And out of the 7 wars fought in this simulation, player 2 always wins. What's the difference? So I started out, the utility of the first player is 500. The utility of the second player in each case is 1000. So why did I choose that? Because to me it seems, I was keeping my eye on the news. To me it seems that Iranian regime is way more resilient than us. So let's give them twice as many utils when they start the game. Right? I'm just playing with numbers. And by the way, if you want to play with numbers, I'll show you. There is a website. Unfortunately, Professor Vestimir, he was not able to come. He's traveling. He actually ran my paper through his AI called Timely. It's like team plus family, you get Timely. And that Timely made 2 things out of my paper. One is a web page, and the other is a comic book. It's really funny. This guy, he's a great mathematician and computer scientist and a businessman too, because he's in this AI business as well, among many other things. But one thing you would find on that web page version of my paper is a war simulator, just like that, but much faster. Because I didn't try to optimize the algorithm. So you can input utilities, you can input incurred losses, and you can run this game as many times as you want. You can play the war and see what happens. So I just did 7 times here, 7 times here. So what are the answers? So here, again, I'm watching the news and I think each time we bomb them, we probably inflict twice as big a damage, right? Why not? So L equals 100. That's what happens when they bomb our bases in Kuwait or wherever they do it. And again, it's not about the war with Iran. It's about any of these wars. And it's not about the United States, and it's not about anything. It's just a very general model. So, okay, if we inflict this big damage, they inflict 100 utils on us, we inflict 200 utils of them, we always lose. So I promised that I can compute all the probabilities at the beginning of the lecture. So here they are. I'll explain how exactly I compute them later in the lecture, but here they are. Our chance to win is 5 times 10 to the power negative 8. Is it a big number? No. Our chance to fight to a draw is 2 to the power negative 8. But don't feel bad for poor player 1. The expected duration of the game is about 1,000 years, if one cycle takes a week. You start seeing why these never-ending wars never end. It's pretty slow. All right, and then I'm like, okay, and what if I cut the number of the amount of damage we cause on the other side by 10? 200 divided by 10 is 20. And I run the same model. All of a sudden, our chance to win is 77%. Yes, sir.
What is a stalemate? Like what condition?
The stalemate is when they simultaneously hit 0. Surprisingly, for random walks, there is an explanation. I probably wouldn't be able to explain it in this lecture, but 0 is a special number. They hit it more often than others. Because theoretically speaking, what is this sort of bridge that your random walk has to cross in order to get to either 0 or negative utils? For the first player, it's 0, -1, all the way to negative L minus 1, right? So this random walk can jump at one of these L numbers. However, it can jump to 0 from 2 positions, by a small negative shift -1 and by a large negative shift -L. And to all others, it can only jump by means of this large shift -L. And that one has a very small probability. So 0 appears more often than others. As the stopping utility point 0, 0 appears more often than others. so it deserves special treatment. That's why. Thanks for asking, very good question. So if you look here, and let's look at the results. So here, I, as a first player, inflict 10 times less damage on my opponent each time I drive through. And my probability switches from 0 to 77%, my probability to win. And my probability for a draw switches from 0 to almost 1%. And the expected duration of the war is only 357 years. So it looks way better, right? Now, here comes this paradox. To win this war of attrition, where each round is a game of chicken, you have to minimize the damage you inflict on your opponent. Just let it sink. It's weird, right? For the first look. Actually, if you give it a thought, it makes sense. But when you just first have discovered it, it's like, huh? Really now? So, however, of course, you can think if it helps, even at the level of simulations, if it helps to set m equals to 0 to minimize m, why don't I set m equals to 0? You can't. Two reasons. One reason is setting m equals to 0 means you quit, and therefore you lose. And so that's sort of from the common sense point of view. And from the point of view of this model, both L and M are much greater than 1. Remember, that was one of the setting points for the game of chicken when we played just one round. So basically, you have to minimize the damage to prolong the war and to make your opponent quit as much as you can subject to the restrictions without quitting the war. So the way to win is to keep some very low intensity warfare forever and ever, until something happens. And all of that is actually proven as theorems in the classical setting. And that's why we have these forever wars. So getting back here, so there will be a little bit of math. I was thinking how to keep the level, it's not completely a public lecture. It's a lecture for graduating math circle seniors, and they know enough math for me to kind of tell them, to kind of dig a little bit deeper into that story. So I hope everyone now understands that u1 of k and u2 of k, they just explain the x and y coordinates of that two-dimensional random walk. And everyone understands that this random walk stops when the first of the coordinates hits 0. And it can happen so that both of the coordinates hit 0 and the random walk stops. So now, what is the expected drift of this random walk? The expected drift is another important feature of any random process. Where did I put eraser? Is that it? Probably. So what can happen in one step? In one step, so let me just do this computation for you. So how do you compute this one? Well, with probability p times q, there is no change. It's 0 times pq. Because with probability 0, both players chicken out, and utility doesn't change. And I'm looking at the first player. So they can lose one util, so plus -1 times, what's the chance of you losing one util? P times 1 minus q. Plus +1, they can gain one util, and the chance is 1 minus p times q. Plus, they can lose L utils, and the chance is 1 minus p times 1 minus q. Well, let's see what this computation gives us. I mean, I actually did this computation over here. This is what it gives us. It's kind of obvious, but why not? So the 0 times anything disappears. So here I have negative p. So negative p plus pq comes from here. What do we have here? Plus pq, plus q, I'm sorry, plus q minus pq, and minus L times 1 minus p times 1 minus q. So positive pq and negative pq cancels out, and you have negative p plus q minus this number. So this is what you expect at one step for the x coordinate. And the similar computation, absolutely symmetric, switch P and Q, replace L by M, and you get the same drift for the second player. And now, knowing this, let me introduce one more notion. It's called, from game theory, it's called best response surfaces. So I'm player one, and I'm looking at this expected drift. And look, there are two variables here, P and Q, but Q is not under my control. My opponent can choose their frequencies of driving through versus checking out. The variable under my control is P. And I can choose P as to attempt to maximize my drift, to make it as positive as I possibly can. So how do you do this? It's kind of it is an optimization problem, but a half of the variables are not mine. I cannot use them. So there is only one variable that I can use. So, you know, I take partial derivative of this expected drift. So I just ask myself, for what value of P would this rate of change with respect to P be equal to 0? Because if it's not equal to 0, then I can optimize locally and I can get a better outcome for myself if changing P slightly this way or that way. But if this is equal to 0, then I can't, and this is a candidate for that Nash equilibrium. So let's see, if I differentiate with respect to P, what do I get? The derivative of negative P is negative 1. Minus L times 1 minus Q. And what do I have when I differentiate here? I have negative P. The derivative of that is 1. Set it equal to 0. If I get an answer different from the one on the slide, then I messed up a little bit. I hope I wouldn't. So what do I have? I have negative 1 minus L plus LQ equals to 0. So I probably did mess up. Oh, no, I don't think so. So what is it? L plus 1 equal, no, I did someplace. Something is wrong with the sign. Okay, let's catch it. So, oh, of course. Oh, no, the derivative of negative P is negative 1. So, and here is, oh, it's plus here, obviously, yes, because it's negative and negative. Yeah, okay, now it makes sense. Yeah, okay. So let's see. Negative 1 plus L minus LQ equals to 0. So L minus 1 equals to LQ. Q is equal to L minus 1 over L equals to 1 minus 1 over L. And that's that Q hat. And you rediscover in a different way that optimal value for the second player that makes me indifferent with regard to my choices. So you can find Nash equilibrium in two different ways. Either the first way that I did in the lectures is called the equilibrium principle, and that's how people in economics do it, or this way, and that's how people who know calculus do it. So why is this way needed? Because that way seemed to be easier, kind of more intuitive. The reason is when we switch to quantum stuff, and I'm not sure we're gonna have time for it in this lecture, but if you switch to quantum stuff, then best response surfaces become a messy combination of trigonometric functions, sines and cosines, that depend on phases and this and that, and then the equilibrium principle stops working. But you know, you can always take partial derivatives, get best response surfaces, and numerically find all the Nash equilibria needed. So, but you get the same answer. Here it is, the expected drift for the first player. So now you take that probability, P hat and Q hat, plug them in here, in here and here, I'm sorry, you get the expected drifts. Negative 1 over L for the first player, negative 1 over M for the second player. What does that mean? It means that on average, your random walk, the x-coordinate of your random walk drifts towards 0 at this speed, and the y-coordinate of your random walk drifts towards 0 at that speed, on average. So here comes a very useful heuristic. Now imagine that you are an analyst working for the president, a president of this country. If you don't like this one, could be another one. And they say, hey Seth, what am I gonna do? Who's gonna win? You already can say. Because look, your original x coordinate is u1 of 0, right? And you run out of x at the speed of -1 over L, right? So -1 over L times t, the stopping time of the game, so minus t over L equals 0. That's where player 1 runs out of utils. That's when the second player runs out of utils. Well, let's solve. Anyone can solve these two equations, right? So that's T1 and that's T2, because right now I'm looking at these two random walks uncoupled, separately. So it's T1 and T2, the stopping time of the first random walk versus the second time, the stopping time of the second random walk. Why do I call it heuristics? Because the computation of the actual expectation of the stopping time is much more tricky. But this is why they call it heuristics. It's the answer you can do by means of a really easy computation on a piece of scratch paper, and it works actually. It works well enough. So let's see what it is. What is T1? T1 is approximately equal to L u1 of 0. What is T2? It is approximately equal to, what is it? M u2 of 0. So now you want to outlast your opponent, so you want T1 to be greater than T2. So you want, what is T1? You want L1 u1 of 0 to be greater than M times u2 of 0. L is not a variable under your control, unfortunately. I'm sorry, Mr. General. That's their choice. But M is. So what do we have? We have M is less than L times u1 of 0 times u2 of 0. So what can we control? We can control this variable, and we can control that variable. This is some kind of war preparation, and this is the damage that we inflict on the opponent. Now the war already has started. I cannot choose a change u1 of 0 either. So what's my advice? Minimize M as much as you can without quitting. It popped up in simulations. It pops up in this heuristic. And then I prove it as a theorem with precise values, all that. So any questions about this page? Yes, please.
So is M and L describing the amount of damage you inflict on the other person?
Yes. So if you and I are fighting, so I'm player 1, you're player 2. So L is the amount of damage you inflict on me, and it's your choice. For me, it's a parameter of the game. For you, it's a variable in your control. And M is the amount of damage I inflict on you. And that's the order: L player 1, M player 2. And it turns out that to win this fight, where we both play the game of chicken many, many times, it's best for me to minimize the amount of damage I inflict of you, subject to not quitting.
Well, I suppose you will be applying this to the current ongoing thing with Iran.
No. It's not a political lecture. Look, it's a very general model. You can apply it to the previous war in Afghanistan, Iraq, wherever. Any of them. You can apply it to this non-stop war that Israel has in the Middle East. Same thing. Ukraine is different because both sides, because it's 3 sides, not 2. Ukraine, I think, is just a chessboard where the West is playing against Russia. But look, that's the point I'm trying to make. I started analyzing this because the war in Iran seemed to be unprepared, you know. It's just like game of chicken seemed to be weird for me. But then I realized that the underlying pattern is way more general. It explains many more things that I have asked for.
And when you win when you're like T1 is greater than T2, as in you outlast your opponent. Is that
Yes, because who wins the war? And again, this is a heuristic because I consider these two random walks as two separate random walks right now. But in fact, they're coupled. And actually T, the stopping time of the game, is the minimum of T1, T2. And each of T1 and T2 is a random variable. It's not deterministic. It's a random variable. So the actual computation is way more involved. I'll do it for you later. And I have answers to all these questions precisely. But here is a heuristic for you. If they just ask you, given a piece of napkin, who wins, this is what you do. You compare this number to that number. Whichever is smaller, that opponent outlasts the other side and wins. If the war is a multi-round game of chicken. Let me first switch over here.
How do you define winning? Is it when you surrender or
No. There is
stop
no such thing
fighting,
as surrender. It's too
or-
complicated. This is a very simple game. So you and I start fighting. How do we fight? I am player 1. I have some original number of utils, u1 of 0, whatever that number is. You have u2 of 0, right? Then, once a week, we play the game of chicken. And the number of utilities that we have, depending on what we do, is increases or decreases by the numbers given in that table, right? So suppose you drive through, I chicken out this week, you gain 1 util, I lose 1 util. And it's a random walk in the plane. Or we both drive through, then you lose m utils, I lose l utils. But the first of us to run out of utils loses the game. And if it happens so that our utilities both hit 0 simultaneously, then it's a draw. Does it make sense?
A little.
All right, there was one more question over here.
Thank you. Okay, so just real quick on this slide.
Even if real slow, go for it.
Okay, so you're trying to maximize your expected drift, right?
No.
Or you wrote
Each
that.
of the players,
Yes.
not me, each of the players tries to maximize, move to the right as much as possible, the expected drift. Yes.
I see, but the parameters in control of U1, for example, are M and P, right? Not Q. But when you...
Hold on. M, so P and M is the same thing. P is the probability before you start playing rationally. When you start playing rationally, you compute P to be equal to 1 minus 1 over M. So P hat, P disappears. You find P hat, and that is M minus 1 over M. And they find Q hat, and that's L minus 1 over L. And then you replace P and Q by those numbers.
I see, but by your computation, the derivation of the optimal Q hat comes from optimizing player 1's expected drift.
Yes. So you see, I just find the best response surface for me, right, as player 1. And how do I do that? I take this partial derivative, set it equal to 0, and in the PQ plane, so this is P, this is Q, this is 1 because they're both probabilities, right? The best response surface for me is, where is it? Q, sorry, Q is equal to 1 minus 1 over M. It's this straight line in that square.
I see.
But for my opponent, it's this straight line, 1 minus 1 over L. And that's where they intersect. You get the same pair of numbers that we got doing this Nash equilibrium computation at the beginning.
But in a sense, then, aren't you optimizing for their expected maximum drift? Because if
No. Good question, but no. It looks so, but no, it's not. Because when I get this best response surface, for any point, BRS is called best response surface, for any point of the surface, the part of the gradient that I control is 0. So I cannot improve locally for any point. Although it looks like I'm optimizing for them, no, I'm optimizing for myself. And generally, when you switch from classical to quantum, in classical, everything is linear, nice and easy, breezy, lemon squeezy, whatever. But in quantum case, you cannot compute those points analytically. You can just describe best response surfaces by means of taking a lot of partial derivatives of a lot of complicated functions. You get something varied sines and cosines wherever they intersect. These points are suspects to be Nash equilibria. But finding Nash equilibria is not local optimization, it's global optimization. But to be globally Nash optimal, points have to be at least locally Nash optimal. So then you just check all these points one by one and see which are and which are not Nash equilibria. And we actually do it. We already have a quantum calculator that does that numerically. When I say we, there are two undergrads, Nishans and Jessica, aka Rengxin Lee. You probably know them. They are our instructors. They couldn't come today. but they have done it already. We already have this quantum calculator, where we use this idea in much more complicated analytical setup.
Thank you.
Well, thanks for asking. So let's move on, right? No more questions? Okay, let's move on. So now let's take a quick look at these simulations. Now you start understanding what I have done, right? So I came up with some math that I'm proud of that actually precisely computes these probabilities and the stopping time for that coupled random walk. And as predicted by heuristics and whatever, the smaller damage you inflict on the opponent, the more likely you are to outlast them in this multi-round game of chicken. So here comes the main computation. I'm not sure it will stay in our YouTube video because this is the only place where I'll go a little bit math heavy, and I'll just watch it. I'll watch the recording and see whether we need or need not to put it on YouTube. So here, it's not super hard, but at least I want to show you that yes, indeed, I have all this figured out and proven. And the math that appears is actually very pretty, but not very elementary. But again, when I say not very elementary, any student from our Advanced 2 or Advanced 3 class would be able to understand. Half of the students from our Advanced 1 classes would be able to understand. Strong undergrads would be able to understand. Any grad student, if they're a math or computer science or physics major, would be able to understand. So, and if you are not from STEM, suppose you are a parent and you're not from STEM, you may not be able to fully understand, or you may, I don't know. I'll try to explain. It's not super involved, but it's a little bit harder on the math side of things. I just want to show you that I have invented a method that really works and enables to compute answers to all of these questions in the classical setup and somewhat in quantum. So why h? What is this function? It's called a harmonic function. So what I'm trying to compute? I'm trying to compute the probability for player 1 to win by means of what? By means of outlasting the second player. So I'm trying to compute, to be more precise, now I can formulate what it means. I'm trying to compute the probability that the first random walk, if played separately, outlasts the second random walk. The second random walk dies first, right? So how do you compute such a thing? Well, here it is. First of all, this is u1, and this is u2. These are all integral points. So it's just, for example, over here, the value of this point, x is equal to 0 and y is equal to 1, 2, 3, 0, 3. So if we are here, what is the probability that the first player has outlasted the second? 0, right? The probability. So I have to put the number 0 in here because the first random walk has run out of utilities. u1 is equal to 0, but the second random walk is still breathing. So if the game ends up at this point, this function that I'm looking for, h of x, y, and h is the first letter of the word harmonic. So this function is called the harmonic function, and why it is called that way, I'll explain in a moment. But if we are here, then the value of the harmonic function, so h of 0, 3 must be equal to 0. Because the probability of the first player outlasting the second player, if we are here, is equal to 0. And so it is here, here, here. Here is a draw, but still the first player didn't outlast the second. So, and any point here, x is already negative. Y is still breathing, still positive. How about down here? So everything in here, the value of my function is 0. Now, how about here? And again, of course, I can do things much faster, right? But I just want everyone in the audience to see how you can play with it and figure out that equation and solve it and see that all the things that I state actually have proofs. Everyone can do that. So if we are here, the x-coordinate is 1, the y-coordinate is 0, which means the utility of the first player is 1, the utility of the second player is 0, so I put probability 1 over here. H of 1, 0 is equal to 1. because the probability, if we are here, the probability of the first player to win is 1. They have won already, right? So you write down the boundary conditions, which are actually here. The value of your harmonic function is equal to 1 if the first variable is strictly positive, and the second variable is less than or equals to 0. And it is equal to 0 otherwise. So you have boundary conditions. So where does the equation come from? The equation comes from the very description of the random walk. So let me switch back 2 slides back here. So imagine I am someplace here, and the coordinates are x and y of this point, which means u1 of k equals to x and u2 of k equals to y. K again is the time in weeks, and I'm someplace here on this integral point of this 2-dimensional lattice. So what can happen to me? This probability, so what is my probability to outlast as player 1? What is my probability that T1 will be greater than T2 if I am here? And of course, I can think of x and y as the original utilities, u1 of 0 and u2 of 0. So I can, this probability PQ, I'll stay here. So I take one step. So it's going to be PQ, and this probability is actually my function h of xy. So h of xy, and let's keep it away from that. H of xy equals to PQ times f h of xy. Because if I take one step with probability p times q, I end up at the same point. And then my probability to times my probability to win if I am at that point here. Plus, look, if the first player chickens out, the second drives through, then the chance of that happening, then what happens? X decreases by 1, y increases. So x goes down, y goes up. So I move here, and that happens with probability p times 1 minus q. So I move from this point to that point. So with probability p times 1 minus q, I now am at the point x minus 1, y plus 1. And similarly, I can move here. So with probability 1 minus p times q, I'm now at the point x plus 1, y minus 1. And finally, I can take a big jump from here, someplace down here. So with probability 1 times 1 minus p times 1 times 1 minus q, I am now at the point x minus l, y minus m. So this equation shows how my probability function doesn't change when I take one step. So is this weighted sum over this 2-dimensional lattice or the graph of that game or whatever it is, it can be generalized. So since the value of the function at this current point I consider xy is some weighted average of the neighboring points, functions having this property, they're called harmonic. And if your lattice is nice enough, and of course here this big jump ruins the symmetry, then you can take the limit and you will get classical harmonic functions, which are the kernel of the Laplace operator, but we don't need that. So basically, the value of my probability at any point x1 is this weighted sum of probabilities at neighboring points, which is the same point, 2 points on the diagonals, on this diagonal, and the point below this diagonal. So now you have this, it's not one equation. For each pair x and y, you have its own equation. So if you have infinitely many linear equations with infinitely many unknowns and with boundary conditions here. So now, if you take that value p hat and q hat, because both players are playing rationally, so you take these values, p is equal to, remember, p is equal to 1 minus 1 over L, and q is equal to 1 over m here, 1 over L here. If you plug them in, you'll end up with this equation. You simplify as much as you can. You get this, m plus L minus 1 times h of xy plus 1 minus m times h of x minus 1 y plus 1 plus 1 minus L times h of x plus 1 y minus 1 equals to this. And that is that harmonic equation for that function that I need to solve. And if I solve this equation, then for every point x, y, for any pair of the original utilities u1 of 0, u2 of 0 in the positive quadrant of that plane, I will know the chance for the first player to win. Does that make sense? Awesome. So how do you solve it? Here I'm a little bit proud. I found the trick and we discussed it with ChatGPT Pro extensively, and it said that it didn't find anything analogous on the internet. So I think I'm the inventor. I may be wrong, but for the first time in my life, I always write, of course, I would like to thank such and such people for useful and productive and stimulating conversations. So this time it's Professor Rahul Roy from our physics department, it's Professor Salman Avestimer from USC Computer Science department, and it's ChatGPT Pro. But they say, the computer says that they haven't seen that trick. So let's see what the trick is. Yeah, so I claim that the way to solve this system of infinitely many equations with infinitely many unknowns is to recursively solve systems of linear equations. So I claim that you just have to recursively solve, oh yes, red is better, the system of linear equations. an times hn equals to rn. For n equals to, recursively, 2, 3, so on and so forth, or u1 of 0 plus u2 of 0. And then you find them all. Where an is this tridiagonal matrix. And of course it comes from that equation that I just have erased, this harmonic equation. You've seen those numbers on the board. Now what are the h's? hn of x is just h of x n minus x. So y is equal to n minus x. So you just take the nth diagonal, and you know that the points where it hits the axis, here the value of my function is equal to 0, because look, x is already 0, y is 1. The second random walk is still alive, the first has just died. So the probability that the first player outlasts the last is 0. So h of 0 n is equal to 0. h sub n of n0 is equal to 1. So these are the boundary points. And then there is a bunch of points here. So this is hn of 1 n minus 1 is just h of 1 n minus 1. But on this diagonal, there are n minus 1 variables, because this is not a variable, this is a known boundary condition. This is not a variable, this is a known boundary condition. The variables are h of 1 n minus 1, h sub n of 2 n minus 2, so on and so forth, up to this point, which is h sub n of n minus 1, 1. So these are the variables, and they're all listed here. And then you apply this matrix to that set of variables, and you get the right-hand sides. The right-hand sides are already not variables, they're already numbers. Why do I say already? Because the big jump, minus L minus M, pushes you down, L plus M diagonals down, where you already have all these variables figured out, right? So you already know these are all numbers for you. And finally, this one comes from the n equals 1, x equals n minus 1 term of the equation. You can check. So this matrix appears in various areas, tridiagonal matrix, in various areas of mathematics very often. It's well known, the determinant is not equal to 0. So this system of equations has a unique solution. And then you just go recursively from n equals 2 to n equals 3 to n equals 4 to n equals 5 until you reach this diagonal, u1 of 0 plus u2 of 0. In my simulation, it was 500 plus 1000, 1500. And it's not a big job for a computer. And then you know them all. You know all the probabilities for P1 to win the war by outlasting P2. Should I do math, or was it enough? Enough. Okay. I want to cut short on math because, again, it's very hard for people to get into such things in a room where AC is not functioning. So if you get interested in details, email me, I'll email you the paper with everything written down. So let's get back to sort of common sense stuff. So here, I actually do a little bit more heuristics, and I talk about the martingales and how they enable me to do heuristics. I'll probably skip that part in the lecture. Again, if you are interested, feel free to request my paper. But I think it's a good joke. I don't think I would make this T-shirt for everyone. I'll make it for myself. I have no memory. I'm a martingale. In case you don't know, a martingale is a random walk that has no memory. Its expected value at the next step is its current value. And I use this stuff a little bit to play with random walks, but as I just promised, no more mess. Let's skip that. So heuristics, and you see this formula, which I already have explained earlier in the lecture. So I just derive it in a more math-heavy way. And here are sort of like common sense conclusions. The best way to win is not to fight. Set m equals to 0 and you win. But oh no, you cannot, because m is supposed to be much greater than 1. From the point of view of mathematics, there is an obstacle. The model stops working. From the point of view of common sense, if you stop inflicting any damage on the opponent, you lose the war, and that's exactly because you quit, and that's exactly what they're waiting for. They wait for you to quit. Low intensity warfare is the solution. Like what? Like a blockade, right? And that's exactly what they're doing. So now note that this model, it knows nothing about politics, about upcoming midterm elections, about Iranian economy in ruins, nothing. All it knows is that each of the players plays this multi-round game of chicken, and that's predictive power for you. Yes, sir.
Can you explain how the game of chicken models war? Like, I presume drive means attack and stop means don't attack, but like, why is the payoff matrix the way it is?
Yeah, look, just watch the news. Like I'm watching the news now 3 times a day to make sure that the model fits the news well. So first, player 1 has. So again, why am I so fixed at this war in Iran? Because it's closer to us in time. But you can pick one of the recent wars: Iraq, Afghanistan, Iran. You tell me. Which one do you like more?
I don't like any of them.
You don't like any one of them. I mean, like, not in the sense that like you like the war, but like you like me to kind of analyze it.
Sure, like with Iran. I guess my question is like, why is it that when both attack, that's a worse payoff than when I get
because
attacked?
Look, once this war is started, right? What do? Either side cannot attack with full force. If, for example, we take this ongoing war with Iran as an example, the event that has triggered that war was that uprising of Iranian people against the ruling regime, right? So what did the administration here say? We want to help Iranian people. Whether it was sincere or not, I don't judge, right? It's not my job as an analyst. I stick to facts, not my beliefs or my biases or whatever. But the statement was, we want to help Iranian people free themselves. It actually will benefit us a lot. They didn't say it out loud. It was in parentheses. Probably, I don't know. So what happened then? It took them time to bring all the hardware to the region. Then they start that war. And once it has started, they realize that it doesn't make sense for them to fight with full might. Because the United States, without Israel, without any allies, can win this war in one day. Just destroy all the power stations except for the nuclear one. What's going to happen? There is very little drinking water in the area. They have desalinating plants. Desalinating plants take a lot of electricity. So big city dwellers will die out of thirst like in 3 to 4 days from that moment. Now they are the people who are most supportive of the regime change in Iran. That's number one. Number two, no administration, no general here in the West, not just in the US, anywhere cannot do such a thing. He will be declared a war criminal and put in jail. You can call it, like whatever, good thing or, short-sightedness, whatever. You like it, you hate it, it's a fact. So the United States cannot fight with full force, right? They're very limited. They cannot make the moves that can really help them win the war. Iran also cannot fight with full force. Because if they do something that would really make people in this country seriously angry, then the United States would be able to use much more force. So each side is forced to play this game of chicken. It's more posturing than real fighting.
I guess I just don't understand how the payoff matrix of chicken relates to the war. Like, why is it that we're justified, like, our payoff is justified in going using full force if they don't. Whereas, like if we both use full force, there's a horrible negative for us. Like I feel like the payoff for they attack us and simultaneous attack should be similar, but there's like a huge gap here.
First of all, you can respond. You can set your M equal to L and see what happens. And of course, the game is symmetric. Then, depending on the original number of utils, if everything is equal, then probability is 50%. Second of all, you see, the thing is, it turns out if you're not allowed to fight with full force, according to this model, then you try to win not by destroying your opponent, but by outlasting them. So imagine for a second that this administration rules this country for the next 1,000 years, right? Whether you like it or hate it. And this blockade stays in place, and the warfare is very low intensity on our side. Then the model says you have a chance to win, right? Because the public opinion doesn't happen. Once a week we drop a couple of bombs someplace else on the other side of the globe, right? It doesn't, and we are already used to high gas prices. Okay, it was $4, now it's $6. Who cares? It's already for 1,000 years, right? So Iran would probably run out of their missiles and drones and bullets in 1,000 years, and we're going to win. So you see, the goal of the game becomes not to destroy your opponent, but outlast your opponent by making them spend all of their utils while you still have some. Does that make sense?
I think that the conclusions make sense, but part of the question I think Marcus was getting at was, what is the decision that you're actually making every week? Like, is it just attack with full force? Like, what is the decision every week that you make that the game of chicken models?
So look, again, if I am an analyst and you are a general, I would say, sir, my advice is low intensity warfare, you decide what it is. Blockade sounds good to me, and spend as little effort as you possibly can to keep this war alive until they run out of their utils. And then you win.
Like, so I have probability P of doing something. What is that something?
The probability, so okay, you're player 2, I'm player 1, right? I maximize my probability of outlasting you. You will run out of utils earlier than me. So my chance to win increases when the chance for my random walk to outlive your random walk becomes bigger and bigger. So I'm playing for outlasting you. You will run out of drones and bullets before I run out of public support here. That's the game I'm playing.
But in like the game of chicken, right, we have a P and a Q, like you're choosing whether or not to drive or to chicken out. What is the equivalent for the warfighting scenario? What are you choosing
They both
between?
choose to drive through.
But what is, like, driving through is the analogous thing in the game. What does it mean?
So right now we may be seeing the beginning of a round, right? Iran is not happy about something Israel is doing. I don't remember whether it was in Lebanon or in Gaza. So they just launched a few missiles, right? So now Israel is a wild card. So they may respond, and Americans may be forced to respond. But my prediction is it's not going to be all out on either side. And already Iranians can actually destroy a large part of Israel if they fire many of their missiles simultaneously. Why don't they? There are some physical limitations, but mostly they're afraid of response of the other side. They don't want to inflict too much damage, whether consciously or more likely intuitively. I don't think either side knows about my model, right? Yet. I'm going to publish hopefully soon. But what their gut feeling is, we cannot win by, bombing American bases or Israeli bases. We have to outlast them. We have to nullify their public support. So we fight this game of chicken, round after round after round. Does it make sense? Oh, there is a question over there. Could you please pass the mic? And again, it's my interpretation, but you see this model. Math doesn't lie, and I have proofs. Yes, please.
With regards to the probability and how it
Nate, is that you?
Yeah, hey, what's up, Oleg? With regards to the probability, if we're in a 5-round boxing fight, and before the fight, I think I have experience looking at other fighters and understanding them, and I look at you, And I think before the fight in the first round, the probability that you can jab better than me is this, and the probability that I can cross better than you is this, and we enter the first round. And then it comes to my surprise that you're not only, your ability is a much higher percent, but it reveals to me that my ability to predict is not what I thought. And then that connects to my confidence and my ability to seize the initiative. So as each round progresses, how do you adjust for the probability of your ability to predict the probability, you know what I mean? And then as that affects my confidence or your confidence and seizing the initiative versus being on the defensive, how does one account?
Great question. So before I answer, can you guys guess this guy's occupation? Anyone? Mathematician, physicist? You're looking at the former Muay Thai world champion, Nate DeLong.
What's up, guys?
He is also a science fiction writer, and he also, takes part in movies. Anyway, that's a great question. So what makes my model very simple is that L and M, the damage we inflict on each other fighting, is the same in every round of the game. Of course, you can make it depend on time, either based on the history of the fight or on intelligence assessments. And then this model will still be working, but it will be way more intricate and well more adequate. Question is, why didn't I do it? Actually, ChatGPT Pro can give me intelligent assessments for both US and Iran with a click of a button, maybe a few. I can do that, you can do that, but I actually intentionally kept that model so elementary as to show its power. Being as elementary as it is, it still gives meaningful predictions, which you can check watching the news like for the next month. But yes, of course, if I'm working for the Pentagon for real, I would be changing L and M based on intelligence assessments like every day. And if I'm fighting with someone, I would be changing my tactics and my tricks based on how they react. But here, I specifically chose the most elementary model that already works to show the power of even more elementary mathematics in predicting the future. Thank you, people.